Hello, this is Peter Abels, and here is the BoofCV 0.34, 0.35, and 0.36 video summary. Demonstration applications have been enhanced in general, tooltips are now available. Other language support has improved, such as Kotlin is officially supported, Python has been updated, same with processing. Random dot markers are a new type of marker. Stereo visual odometry has been updated. Stereo disparity has also been updated. The Chessboard Detector has also been significantly improved for fisheye images and is now much easier to calibrate. Hough Detector has also been improved for stability and visualization. Point Tracker has also been improved with updates to its visualization, as well as various bug fixes, and I would also like to thank everyone that made contributions. To find which languages other than Java are officially supported, go to BoofCV's website, go to the documentation, and look at the language section and tutorial. You've always been able to call BoofCV from Kotlin because Kotlin is also a Java virtual machine language. However, BoofCV now has extensions for Kotlin which can simplify coding in it. To see some examples of Kotlin specialized code, go to KBoof examples. Right now it's QR code focus. There's also an article which explains things in a bit more detail for Kotlin developers. Right now, the source code itself has the best documentation on extensions included with BoofCV, so just browse on over and you can take a look. There's stuff for geometry, I/O, pixel math, and stuff like that. It's lacking documentation because I wanted to make it easy to change the API in the future and not devote too much effort into that. Most of it's pretty easy to understand if you're already familiar with BoofCV. Feedback and changes or anything are very much welcome at this point. I frequently receive requests to update PyBoof more often, which is BoofCV's Python wrapper. So I finally got around to it. It's now been updated to the latest stable version of BoofCV 0.36. One of the more significant changes is that stereo support is now complete. Also, random dot markers have been added. There's a 3D point cloud viewer also, as I will show you. I will now run the updated stereo Python example and show you a point cloud. Processing also received an update. The update for processing is primarily just making its wrapper compatible with BoofCV 0.36. The only really new feature that's been added is access to the intensity information inside the template API because that was specifically requested by someone. As usual, everything you see here can be downloaded and run from the demonstration applications. To do that, just follow the links like I am right now, unzip the jar, and then launch the jar as you usually would. There's also a README to give you some additional information about launching it. A completely new type of marker has been added to BoofCV, random dot markers. These markers are designed to provide a 3D pose estimate, be uniquely identified, and robust to occlusions. How robust it is to occlusions is one major improvement over other markers in BoofCV, as you can see from these examples. You can also detect a lot of markers inside a single image reliably. So how do these markers work? Well, what happens is I first identify inside the image these dots. That is done using a contour finding algorithm and looking for circle-like objects. Once circle-like objects are found, all their neighbors within a local radius are found, and then from these, a hash code is computed. The hash code is done by looking at the relative angle of these landmarks. Once you have a few landmarks, it is then possible to identify one of these markers, and then you can, from that, compute a homography and estimate where the rest of the markers should be. As you go through and track these objects, it actually is going through and computing more descriptions to add robustness to different angles. This implementation is based off of Uchiya's paper from 2011, which is also why it's called Uchiya markers. I stumbled into this a couple years ago and I found it really interesting based on how different it was from other marker identification approaches, using angles and computing hash codes. Hadn't seen that. This approach is actually based off of locally likely arrangement hashing, which is typically used to look up pages in the book based on corner locations, and a similar strategy to what I just described. While this implementation is good for a first pass, there are several planned improvements in the next version of BoofCV, such as allowing rectangular markers and allowing it to run faster. Stereo visual odometry got a long overdue refresh in BoofCV 0.36. The most obvious component that was refreshed is the demonstration application I'm showing you right now. It was rewritten completely from scratch. It is now much more configurable in how information is displayed, and most major tuning parameters can be changed in the GUI. You can see the improvements in the side-by-side comparison. In the old view, it doesn't even show the sparse point cloud that's generated from visual odometry, and it lacks many of the controls and definitely does not let you configure the different visual odometry algorithms in any meaningful way. The stereo image pair is shown on the left, with features overlaid on the left camera image up top. When you click on inliers, it toggles that. The meaning of the colors of the features changes. For example, right now it's showing the depth, where the more red colors means it's up closer, while the more yellow colors mean it's farther away. However, if I set it to age, I'll show the track age. So for example, cooler colors mean it's a more recent feature that hasn't been tracked as long, while more purple means it's been tracked longer. In the Kitty data set, track age is even more stable because you're driving in a constant straight line, so in the center view it tends to be older features. The point cloud on the right that you're seeing can also be configured in several different ways for how you view it. For example, the coloration in this dataset is black and white. It's kind of hard to see the differences. However, if you use pseudo color, it's actually sometimes even easier to see the trees in different objects. And there's a lot of different objects for the pseudo color, as you can see in that list that came up. If you hit Control F, I'll switch to a first-person flyby view, where it's always showing you the latest frame. This kind of looks cool, although I'm not totally sure how useful it is for understanding the data set. What I just was doing was adjusting the maximum age. If a point was seen more than that number of time steps ago, it will just not be drawn. So you can only see the most recent events. This can be useful to reduce the amount of clutter. When you change max depth, what you're doing is telling it to only show you features which are closer to the vehicle when they were first seen. This is a good way to remove kind of stereo smear. If you click on the Configure tab, you can now change which stereo visual odometry algorithm is being used, as well as all the inner algorithms and their tuning parameters. This is a great way to rapidly tune and do rapid prototyping if you want to see if a technique can be used on a particular data set. Well, I'm not going to go into details now. There actually are 3 different visual odometry algorithms included in BoofCV: mono, dual track, and quad view. There are a ton of different settings that you can manipulate. It would actually probably take me an hour or two to go over them all and explain everything in depth. However, as I'm showing you now, you can move the mouse over and get additional tooltips. While this won't explain everything, if you are already familiar with a lot of the visual odometry algorithms out there, you might be able to figure out what these different settings are. Otherwise, you're kind of stuck going through the code for now. I am thinking of doing a different video in the future where I'll go through and explain this, or maybe a series of videos. It's been made much easier to open up external datasets. So you do open sequence, and then you select the sequence for the left camera image, like so. I'll show you a preview of the image. Select the right one. I'll also show you a preview of the image. And then you select the calibration. This needs to be in BoofCV format. The original motivation for this refresh is that when originally written, BoofCV did not have sparse bundle adjustment, which was a critical step that every paper at times said you needed. Despite that, when Kitty was first released in 2013, BoofCV had a number 3 spot for a brief period of time, with what was then state-of-the-art performance of 2.3% error per distance traveled. Today, the best competitors have sub 1% error. Unfortunately, BoofCV has since been delisted from Kitty because I never published an academic paper. The reason why that never happened is because it was mostly rehashing of ideas that are out there. Not that that stops most people from publishing conference papers on visual odometry. Most of the stuff is very unoriginal, and it was done back in the 2000s or early 2010s. So exactly what changed in this refresh? Well, all 3 visual odometry algorithms were updated with the latest coding standards, APIs, and algorithms found in BoofCV. This includes integration of sparse bundle adjustment and, when appropriate, multiple keyframes. So after all this work, does it actually do better at Kitty? I've not done the careful analysis needed to answer that question, but all signs point to probably not. It'll probably get around 2.3% distance per hour traveled. One of the reasons for that is that the more optimization you do in bundle adjustment, the worse the results often get. Like one iteration seems to be almost ideal. That kind of goes back to this observation I had a while ago, where when after ransack, if I optimize the results using all the inliers, quite often it got worse. One of the best performing algorithms in Kitty's benchmark explicitly says not to do that. The idea is that there's almost always going to be some false positives inside the inlier set, and those will degrade your results. And also, when you carry results over from the past, that tends to degrade it. However, in other papers, I've seen them do stuff like optimize using 15 keyframes, and they claim like vastly superior results. So who knows exactly what the secret recipe is for optimal performance. The upcoming release of BoofCV 0.37 has a couple additional features involved. Well, not really new features. Some stuff was actually removed in the previous version to simplify the code. Turns out that stuff was actually important. Can I see the README or the change list to see exactly what all that stuff is? Stereo Disparity gained several new features and performance enhancements recently in BoofCV. Block matching approaches can now compute scores using SAD, NCC, and census. Before it was just SAD. No pun intended. After being on the to-do list for several years, semi-global matching, or SGM, has been added to BoofCV with implementations of SAD, census, and hierarchical mutual information, or HMI, along with block matching variants of all those scoring methods. Both block matching variants and SGM fully support threads, which allow them to run much faster. There are also several API improvements, and now everything fully supports the configuration classes. Sparse disparity has also been updated and now includes forward-backwards validation, texture validation, and has a cleaned-up API. The demonstration application has also been significantly improved to include more configuration options and better point cloud support. You can even save the point clouds to files as a PLY and open it in a third-party application now. BoofCV's Chessboard Detector has been steadily improving and is probably one of the more robust ones out there now. The latest improvement is a new X-corner based detector that greatly improves fisheye images and other challenging scenarios. The first stage in X-corner detector is shown here. For each stage in an image pyramid, you compute the X-corner intensity by applying a Gaussian kernel, sampling pixels in a ring, and then computing X-corner score followed by non-maximum suppression. To see the X-corner intensity score, you just need to slide the X-corner slider, and then you will see it. This is also useful when you want to compare the regular RGB to the X-corner intensity. Red means it's a region that thinks it's highly likely to be a X-corner, which occurs between intersection of two squares. After the X-corners have been found, they are connected to each other based on their relative orientation and having a strong line connecting them in the image. To see those connections, you can click on the perpendicular checkbox, and then it'll show the connections as well as their intensity. If you would like to see the X-corners orientation, just click on corners. It'll also give you an idea of how many false positives there are in the image. The first stage of detection of X-corners actually does a pretty good job of removing false positives. See that line going across? That's the orientation. And in order for two corners to be connected, they need to be approximately perpendicular. This new chessboard detector has been tested on a lot of images, especially some fisheye ones. Like for example, this data set here from another paper. There are some very heavily fisheye images as well as noise that's highly structured, like what I'm showing you right now. Notice how this actually lines up and could easily be mistaken for a chessboard. Moving back to the center, one thing I'd like to show you is that there's a potential for being able to detect any grid or any chessboard, even though you don't tell it its size. This opens some interesting possibilities, like being able to use partial chessboard, as well as just like unknown, where you don't need to like do very much. Well, these current results are pretty good. There's still planned improvements for the chessboard detector. Hope to make it faster, and then there also are a few edge cases which need to be addressed. One thing I found when looking at other chessboard detectors is that pretty much everyone overtuned their detector to their own personal data set, which is why this one's being developed using pretty much every chessboard dataset I can get my hands on. Standard Hough line detectors have been recently improved in BoofCV. They offer better stability, two clearly defined families, improved API, as well as improved demo applications. However, as I started to make this video, I realized that there were not enough improvements. So what you're seeing here is actually based off a snapshot of BoofCV 0.37 and not the latest stable 0.36. So there'll be some differences if you work off a stable branch. In order to understand the improvements to BoofCV's detector and the different families, we need to go over a bit of mathematics first. Let's start with a quick refresher for how transform works. A line can be defined in 2D using the following parametric equation, where r represents the distance from the origin and theta is the angle or slope of the line. The first step is to find all points inside an image, which might be a line, and then map each of those points to all possible lines which correspond to that point in parameter or Hough space. From this, you create a 2D histogram as is shown on the bottom right. The peaks inside the histogram represent lines inside the actual image. BoofCV supports two families of Hough line detectors, binary-based and gradient. The input to a binary Hough detector is a binary mask where each pixel represents a potential point on the line. A single pixel can be any line which passes through that point. That means there's a many-to-one mapping. The gradient-based line detector works by also having a binary mask where it indicates which pixels belong to the line, but you also have gradient information. This means that a single pixel fully defines a line. Here's a visual summary of the two types of Hough line detectors in BoofCV. For the binary, you get an input image, and then you need some way to convert it into a binary image. In this case, simple thresholding is used, and then from that, you compute the parameter space histogram. For the gradient-based one, you take your input image, you compute the gradient. From the gradient, you create a threshold image based on the gradient magnitude, and then you take the gradient and the binary image and compute the parameter space histogram. So with the binary method, you can give it any input image you want. However, you need a way to convert it into a binary one. BoofCV out of the box provides an easy mechanism for applying a threshold, as well as computing a gradient and then thresholding that. You could also roll your own using a canny edge detector. Typically, it does work best if you apply Gaussian blur. With a gradient-based method, of course, you need the image gradient, and then you need to compute a binary mask. BoofCV will handle that for you. Works best if you apply Gaussian blur. However, this method is also sensitive to the noise in the gradient image, so you need to take that into account. One advantage of this is that you can apply different parameterizations. There's actually many different ways to parameterize a 2D line. Of interest here is polar, which I've already gone over, and foot of norm. With the foot of norm, it defines a line based on the 2D coordinate of the point on the line which is closest to origin. This has the advantage that you remove some tuning parameters. With the polar, you need to specify how many bins there are for the angle, and then you also need to figure out a reasonable maximum value for r. With foot of norm, you create a histogram that's the same shape as the input image. Those aren't tuning parameters. A major disadvantage, though, of foot of norm is that it has a singularity at 0, which represents an infinite number of lines, and then the accuracy, as I'll show you later on, depends on your distance from the origin. There are some methods to mitigate that, but that's outside the scope of this video. Let's go over a direct comparison between the binary and gradient Hough detector. I've configured them so that they have all the same major parameters. It's just the difference of how the histogram is computed. So comparing the two, it looks like the binary-based one has more false positives. Let's see if we can understand what's going on. When we look at the transform image, we can see that there's a maximum where there really isn't. This is actually not too uncommon. The reason for that is because it doesn't get as much information from each pixel as compared to the gradient one. So it generates a whole bunch of potential orientations, and sometimes these line up and cause a false positive, and those can be difficult to remove. Let's see if we can improve the results by doing a little bit of tuning. Hough line detectors are notorious for being sensitive to tuning parameters. It's better, but still not quite as good as the gradient-based detector. So what are the advantages of using a binary Hough detector, and why is it the more popular of the two? So in many ways, the binary-based Hough detector is actually easier to work with and has fewer tuning parameters. Take this example here. I'm computing the edge and then fitting the lines to that. That actually makes it more complex. Even after tuning, it's not quite as good as I would want. However, if I switch it to a image-based method, so now I'm just thresholding it, I don't have to deal with all those edge-related tuning parameters. The code is actually simpler, although BoofCV handles a lot of the complexity. And this actually gives like a more stable result in this particular scenario. So which one is the best really depends on the scenario you're dealing with. Let's look at parameterization and the gradient Hough detector, since it can support different things. Right now we're using a foot of norm. However, there's some duplication. Let's investigate that a bit. By duplication, I mean multiple lines in the same location. So I can tune that away. I can tune away that problem by adjusting the mean shift kernel size as well as non-maximum suppression radius so that those two lines converge into one line. The foot of norm also has an issue where its accuracy depends on your distance from the center. So look at the histogram distributions, see how it gets more spread out and less distinctive the farther away from the center you are. The reason why the center matters is that the origin was set to that in order to mitigate this issue of accuracy. If it was the lower left-hand corner, then everything in the upper right-hand corner would be very inaccurate. So let's now compare that to the polar notation. So you can see the transform, and then you can look at these blobs, and pretty much independent of where they are in the image, they are equally as distinctive. So while the foot of norm is easier to tune, you got fewer tuning parameters, it has a lot more finicky stuff. There's another algorithm in BoofCV that's not discussed in this video where it breaks the image up into like 4 different regions in order to like avoid the singularity problem and accuracy based on distance from center. What I'm doing right now is using the webcam to show an interesting object. See if you can guess what it is. So if you look at the foot of norm, you know that these correspond to distance from center. So there's multiple lines along 2 axes. It's a QR code. So what you're seeing is the lines formed by the squares in the QR code. Looking at polar notation, this looks pretty stable, but if I switch to foot, you can see these weird diagonal lines going across that seem to intersect the center. That's due to the singularity. So that's it for now on these Hough line detectors. There are additional types of line detectors in BoofCV they should also check out. The point tracker interface also received several incremental improvements in the recent updates. A point tracker detects and selects tracks or points inside an image and tracks them, and it's useful for various geometric applications like image stabilization and visual odometry. The point tracker API has been tweaked in several ways. Each frame is now consecutively assigned a unique ID. There are functions for getting the total number of active and inactive tracks. There is now a lambda that assists in efficiently pruning tracks, and everything else is about the same. For the point track, it now has a set ID, which specifies what type of feature it is, such as a dark or white blob. The frame it was spawned at is also saved, and then point track no longer extends point 2D. That actually had a lot of unintended consequences. The demonstration application has also received several updates. What I'm doing right now is showing tracks from KLT. There are several different types of trackers that you can run in BoofCV for the point tracker interface. Right now, the tracks are being shown as dots of unique colors. This is good if you want to look at it and try to figure out what's happening to an individual track. And as an example, I'm also tuning this right now to try to maximize how spread out the tracks throughout the screen so you don't deal with them all getting tightly packed in the center, which is a problem you can run with KLT if you're zooming in and out like I am here. I just switched over to doing lines. Lines is good if you want to look at from kind of an optical flow point of view, especially if you use the flow coloration, which is what I'm doing right now. These colors now represent the direction and magnitude of the motion. The line is the beginning and end of the track in the current and previous frame. I just changed it to using a different type of tracker. This is a DDA tracker, which is Detect, Describe, Associate. This probably tends to be a little bit more common for visual odometry applications, although KLT does very good in visual odometry also. And I've been tuning it right now to make it more strict in how it does association to get rid of some of those like false associations you see kind of like zagging across the whole screen. A couple of new dashcam videos have been added to the examples list. These videos do a good job showing how optical flow can be used to pop out different objects in the scene. Plus, it looks just really cool. It's kind of like a warp scene in the movie. Another new feature that's been added is the ability to click on an individual track and highlight it. You also see its position and various track state information on the bottom left corner in the text field. This can help figure out a few things. For example, you can clearly see that the track I selected has drifted a lot. It's swapped objects, gone all around. So when you're using these tracks, you have to really be aware of that, and you can't totally trust that it's going to be on the same object at all times. Typically, you can fix that by using geometric validation. There's been a lot of bug fixes and new features actually not included in this video. In general, concurrency has been creeping out throughout the codebase even more, so it's getting faster and faster. JCodec is finally integrated into the library. I also like to thank everyone that's made a contribution in form of code, bug reports, or suggestions, or even just being a user and helping out other people. Thank you.